Empirical formula is nothing but the simplest whole ratio of moles or atoms. Same thing, same ratio we will get. Next question related to empirical formula. 4 grams of copper chloride on analysis was found to contain 1.890 gram of copper and 2.110 of chlorine. What is the empirical formula of copper chloride? Now, even here, if it is given copper chloride exists in two forms, cuprous chloride and cupric chloride, because copper exists in two valencies, Cu plus and Cu2 plus. So we can't be sure whether it is cuprous chloride or cupric chloride until we calculate the percentages and then the molar ratio of the atoms. Approach is very simple. You will form a table. Although even if you don't form the table and you form you get the moles and then simplest molar ratio, that's absolutely fine. But table gives a holistic view to your teacher, and he or she is able to grant you marks very quickly, and that's what teachers love. They don't want to go through every step and then find out whether you have followed the process or not. So in empirical formula questions, it is advisable that you draw the table, and I'll show the columns usually you will use in that table and get the simplest fold ratio. So in this case, we have copper and chlorine. So we will form a table with elements copper and chlorine. And the columns will usually be percentages, atomic mass, moles of atoms, then molar ratio or atomic ratio, and then simplest ratio. This will be the normal approach, and normal columns you will have in the table. Sometimes this percentages column might not be there. You might have already 100%. The sum of masses of all the elements 100, then you don't need to write this one. Sometimes you get normally the ratio as simplest ratio. So one of these columns is missing there. Yeah, but that will depend on the question. But normally, in general, you will have these 5 columns. Particular to this question, we will calculate the percentages. And later on, I'll tell you that even if you don't calculate the percentages, you will get the correct answer. Only the calculation will be in decimals, okay? More decimal places. When you are asked to calculate the percentages, it is about mass percent. So this percent is actually mass percent, and the formula I have already told you in one of the previous classes that mass percent is mass of the element divided by total mass
Yes, sir.
into 100. You will apply this and you will get mass of copper. For copper, it will be 1.890 divided by total mass, that is 1.890 plus 2.110 into 100. That will be the percentage of copper. Similarly, percentage of chlorine you can get, or if only two compounds are there, two elements are there, you can subtract percentage of copper from 100, you will get percentage of chlorine because the sum of all percentages is 100. When you solve this one, you will get percentage of copper as 47.3% and percentage of chlorine as 52.7. Actually, this is slightly approximated, rounded off. If you calculate this one, you will actually get 47.25 here and 52.75. Then you have to calculate the molar ratio. For that, you need to calculate moles. To calculate moles, you know given mass upon atomic mass, it means you need atomic mass for that. So atomic mass of copper is 63.5 and for chlorine 35.5. To get moles, you know what is the relationship. This is out of 100 grams, 47.3 grams copper, 52.7 grams chlorine. moles of copper will be given mass upon atomic mass. Similarly, moles of chlorine will be given mass divided by atomic mass. If there is any confusion, let me know. And remember, the conversion diagram is very important. Here, what we are doing, we are converting mass to moles. And mass to moles is given mass divided by atomic mass. So you will calculate the number of moles if the compound was 100 grams. Out of 100 grams, 47.3 grams copper, 52.7 grams chlorine. Then given mass upon atomic mass gave you moles. Given mass of chlorine divided by atomic mass of chlorine, moles of chlorine. Now, if you see, this is 1:2 ratio simply. You divide the ratios by the minimum one. Minimum one is 0.74. So divide both by 0.74. You get 1, 2. It means the simplest ratio is 1:2, and the empirical formula will be CuCl2. Cu1, Cl2, the ratio is 1:2, but 1 is not written. So the answer will be CuCl2. Understand the table and how you need to progress. Memorize all the 5 columns. If anyone you need to skip, you can, okay, according to the question, but you need to memorize all 5 columns. After the elements: percentage, atomic mass, moles of atom, molar ratio or atomic ratio, and then simplest ratio. This will be the approach in almost all empirical formula questions. Now, I said that even if you don't calculate the percentages, you will get the correct answer. In that case, your approach will be whatever mass is given, you calculate moles from those. So, for example, for copper, moles will be given mass divided by atomic mass. For chlorine, moles will be given mass divided by atomic mass.
Yes, sir.
Okay. You will get some values of moles here, say X and Y, and you will see that this will be in simple whole ratio 1:2. So when I ask you to, I think this question is there in assignment. You can do by any method, whether you get percentages first or you directly calculate the moles and then simplest molar ratio. Answer will be same. Having said that, if you see that in school, if your teacher always follows the approach of percentages, that's what usually is done, then don't follow this approach, because teachers are sometimes very strict. Even if this method is correct, they say, no, you didn't follow my method, I won't grant you full marks. So in that case, follow the chart, follow the table I have given here. Okay?
So,
Yes.
so what we will do if the percentage will not add up to 100?
In that case, most commonly there will be oxygen. The remaining will be oxygen. Okay. So
Okay, so
if it is not given and if it is organic compound, then it will be oxygen.
okay,
Otherwise, in question, there will be a hint that you can get what it will be. For example, if it says that it's an amine and carbon is this much, hydrogen is this much, it means the rest will be nitrogen because it's an amine. Amines are ammonia derivatives.
yes, sir.
So otherwise, there will be a hint, or if it is not given, it will be oxygen.
Okay,
Shivani, yes, we will be doing that percentage part again and again. Okay? So you will get to know in next question. The molecular mass of an organic compound is 78 and its percentage composition is this much. So here percentages are already given. So you will draw the table like that, but percentages of carbon, hydrogen are already given. So you will write those percentages 92.4, 7.6. It is advisable that you write 100 gram here, okay, or 100% here. Because when you write it 100 gram, okay, and 100%, then it means 92.4 is gram, 7.6 is gram. So first you need to convert the percentages into grams. Only then you can apply the formula to get moles, that given mass upon molar mass. If you don't consider this as mass, you can't apply that formula. Okay. In this case, atomic mass of carbon, 12, hydrogen 1. Get the moles given mass by atomic mass. Given mass divided by atomic mass. Given mass divided by atomic mass. And in many cases, you will get approximation. Okay, so 7.7 will be considered as approximately equal to 7.6. Okay. So for example, if you get 1.99, it will be considered as 2. And in many cases, you will get calculations like these. Simplest ratio, you will divide both by the least one. Least one is 7.6. So divide both by 7.6. You get 1.01 and 1. It means simplest ratio is 1:1. Okay. So here approximation will be done while calculating simplest whole ratio. They might not be exactly same, okay, but very close. Now the question is not about empirical formula. Question is about molecular mass is given and you need to get molecular formula. And if you remember in previous class, I told you that when you convert empirical formula to molecular formula, there is a factor by which you need to multiply the empirical formula. And that factor is molecular formula mass divided by empirical formula mass. You will write in examination and test, you will write complete forms. Don't write M, F, M or E, F, M. Okay. Molecular formula mass divided by empirical formula mass. So if empirical formula, in this case, as it is CH, 1:1 ratio means there is one carbon and one hydrogen, 1:1 ratio. Hence, empirical formula mass will be 12 plus 1, that is 13. Is this clear up to here or not? CH
So,
means 12 plus 1. Okay.
so repeat. So can you repeat it once again?
Okay. Is it clear that how we got the empirical formula CH?
Yes, sir.
Right. So if the empirical formula is CH, empirical formula mass will be means molar mass of this one empirical formula will be 12 plus 1, that is 13U. So empirical formula mass is nothing but the molar mass of empirical formula. Okay, both of these are molar masses.
Sir, and will come to be 6 in that case.
Yes, you're right. Okay. Is that clear how we got the empirical formula mass? It is molar
Yes,
mass
sir.
of the empirical formula, which is 13. So this is give. Now we have calculated this is 13, but molecular mass is given 78. So it means molecular formula mass is 78. 78 divided by 13, 6. It means molecular formula will be empirical formula times n. N is 6. Means CH times 6, that is C6. Is that clear or not?
So what if we had the ratio differently, like 2:1?
Then also the same approach.
So C12 with 6 in that case.
Yes.
If it's 2:1.
You will multiply both by 6. It is actually like this. You will, if it appears in exam, you will write it molecular formula is equal to n times empirical formula. Now this formula is applicable everywhere. If empirical formula, for example, molecular formula equals to n times empirical formula. If n is say 4 and empirical formula is CH2, okay, then you will write C4H8.
Or it is the molecular formula.
That is the molecular formula.
So what is N in this formula?
N is the factor by which you need to multiply empirical formula to get molecular formula. Okay. N is the factor by which you need to multiply empirical formula to get molecular formula, and N is given by, from, you can see from this particular relationship, N is actually molecular formula divided by empirical formula, that is molecular formula mass divided by empirical formula mass, that is molar mass of molecular formula divided by molar mass of empirical formula.
Okay.
That will give you a factor N by which you need to multiply the empirical formula to get the molecular formula. So as here you get 6, you need to multiply CH by 6. So you will get C6H6. That is, it is benzene. The organic compound is benzene. Next question. In this question, you have again molecular formula mass is given, and you have been asked empirical and molecular formula. Percentages are given, and first check whether the percentages are approximately equal to 100 or not. It should be 100, only then you will write it only 3 elements, otherwise you will consider the other one as oxygen. So if you add these, you will get approximately 100. It means there are 3 elements only with percentage composition: carbon 24.27, hydrogen 4.07, chlorine 71.65. Same approach here, but I have written only 4 columns because it is approximately simplest ratio what we get. So we don't need to simplify it further. That's why 4 columns only. Atomic
But
mass
it's
of
100.
carbon. Yes, it is 100. Correct. Atomic mass of carbon is 12, hydrogen 1, chlorine 35.5. Divide the masses. So these are masses. Okay, out of 100 grams, 24.27 grams carbon, 4.07 gram hydrogen, 71.65 grams chlorine. Divide these by atomic masses to get moles. It means you have 2.02 moles of carbon, 4.07 moles of hydrogen, 2.02 moles of chlorine. And if you divide all by 2.02,
So then the ratio will be 1:2:1.
yes, you got approximately 1:2:1. It means it is the empirical formula is CH2Cl. CH2Cl. Is that clear up to here or not? C1H2Cl1.
Yes.
So it will be CH2Cl1. One is not written. Empirical formula is CH2Cl. Now the same thing, find the factor by which this formula, empirical formula, needs to be multiplied. That factor N will be molecular formula mass divided by empirical formula mass. And empirical formula is CH2Cl. It means it will be carbon 12 plus 2 times hydrogen 1, 2 times 1, 2, plus chlorine 35.5. It means it is 9.5.
49.5.
So it means it will be the molecular formula mass, which is given 98.96 divided by empirical formula mass
So
49.5
N is approximately 2.
approximately. Correct. So
So then
multiply
we
the
get
empirical
molecular
formula.
formula.
Yes. So molecular formula in this case will be N times empirical formula, that is 2 times CH2Cl, that is C2Cl.
C2H4Cl2.
That is the answer. Just see if there is any problem in any step. Okay, so I hope it is clear. Next one. Here again, percentages are given. Okay,
So
and
can
it
you
is
again
given,
show the previous slide?
yes.
Yes, sir, done.
An organic compound on analysis gave the following percentage compositions: carbon 57.8, hydrogen 3.6, and rest is oxygen. Means you will consider total 100%, oxygen will be 100 minus this. The vapor density of the compound was found to be this much. Find out the molecular formula of the compound. Before I start, there is a relationship between vapor density.
So we can multiply by 2 to get molecular formula.
Yes, correct. Okay. So vapor density and molecular formula, there is molecular formula mass. Molar mass, there is a relationship, that is molar mass is 2 into vapor density.
Yes, sir.
Sir, by molar mass, you mean the molecular mass of
Yes,
the
molecular
compound?
formula mass. Yes,
Okay,
same
sir.
thing. Molecular formula mass, molar mass, same thing. Okay, why I am calling it molecular formula mass? So that I can differentiate it from empirical formula mass. So that's why I am calling it molecular formula mass and empirical formula mass. Both are molar masses. This relationship you need to remember. Molar mass is twice the vapor density. So here, instead of molecular mass, you have been given vapor density, you will calculate molar mass. So molar mass in this case will be 2 into 83, that is 166 U. So molar mass you will calculate. After that, it is same thing what you were doing. You will draw the table, write the percentages of carbon and hydrogen and oxygen. Oxygen will be 100 minus sum of these two.
38.6.
Yes, correct. So it will be 38.6. So again, out of 100 grams, you will have 57.8 grams, 3.6 grams, 38.6 grams. And you will follow the same approach. Atomic masses of carbon, hydrogen, and oxygen 12, 1, and 16. Divide the mass by atomic mass to get the moles. So you got these many moles. From here, you will try to get the molar ratio. Molar ratio, you will divide by the smallest one is 2.41. So divide all by 2.41. So here you get 2, 1.49 and 1. 1.49 is actually 1.5. And this is something you can simplify. If you multiply all by 2, you will get simple whole ratio. 2 into 2, 4, 1.5 into 2, 3, 1 into 2. Is that clear? 1.5 is close to 1.49. So that's why approximated. And then to get simplest whole ratio means integral ratio as whole numbers. We can convert 1.5 to a whole number if we multiply this by 2. So it means we will have to multiply every mole by 2. Sorry. So empirical formula in this particular case will be C4H3O2. C4H3O2. Write the empirical formula. C4H3O2. Empirical formula C4H3O2. And molar mass, that is molecular formula mass, you had already calculated 166 U. Calculate empirical formula mass so that you can get the value of N. It will be 4 into 12 plus 3 into 1 plus 2 into 16 from here.
Sir, can you please show the previous slide for a second, sir?
Yes.
Mm, yes.
Okay, sir. Okay.
So from here you will get 48 plus 3 plus 32.
So, so please show the previous slide once again.
Yes,
Bhai, loved.
83U.
Okay, sir.
Okay, C4H3O2. So we calculated the empirical formula mass. C4 means 4 times 12, H3 means 3 times 1, atomic mass of hydrogen 1, and 2 times 16, atomic mass of oxygen. And we got 83. The factor by which we need to multiply empirical formula, yes,
Then how do we got molecular formula mass?
that's a good question. Molecular formula mass is equal to twice vapor density, the formula, 2 into vapor density. Were you connected when I explained that?
No, sir.
Okay. So molecular formula mass or molar mass is twice into vapor density. So 2 into vapor density 83, that is 166U. Is that clear?
Yes.
You need to remember that formula for that. So the factor by which empirical formula needs to be multiplied to get the molecular formula will be molecular formula mass divided by empirical formula mass, that is 166 divided by 83, that is 2. It means molecular formula will be 2 times empirical formula, that is C4H3O2. Molecular formula will be C8H6O4 here in this case. Any confusion, let me know. If there is any problem, you were not able to understand any step.
So please explain the last step once again.
Last step is molecular formula is n times empirical formula. This is what I applied here and here, both places. From this, I got n equals to molecular formula mass divided by empirical formula mass. So I got the value of n. Then I multiplied the empirical formula by the factor n to get the molecular formula by again applying this relationship. Is that clear?
Yes.
So molecular formula is equal to n times empirical formula. Value of n will be a natural number. It can be 1, 2, 3, 4, like that. Okay. It can be 1. In that case, empirical formula and molecular formula will be same. Just to understand how we calculated the empirical formula, this is how we calculated the empirical formula. Same 5 columns I have used. And once I got the empirical formula, I calculated empirical formula mass. Why I calculated empirical formula mass? Because I know molecular formula mass, which is twice into vapor density, 166U. And I calculated the value of empirical formula, as I know that empirical formula is C4H6, sorry, C4H3O2. From here I got 83U. And molecular formula mass I calculated from relationship 2 into vapor density as 166U. Now I know that value of n is molecular formula mass divided by empirical formula mass That is 166 by 83, that is 2. And this is actually the value by which I need to multiply the empirical formula, this formula, to get the molecular formula. So I will multiply this empirical formula by 2 to get the molecular formula, which will be C8H6O4. If any step is not clear, let me know. Okay. Yes, Devyansh Chacho, correct. Okay. So if that is clear, then we move to ways to express concentrations. Although there are different ways, density also, okay, mass volume also. I'll discuss 4 because these are which are asked, and the questions will be based on these 4. The first one, remember what is concentration? For example, density. Density is gram per ml. How many grams will be in 1 ml? So if I have 1 ml of something, say I have 1 ml of water, and I weigh this one. So how much it will weigh? That is actually the density. If I have 1 ml of, say, something else, honey, for example. So it's honey is heavier than water, right? So its weight will be more than 1 gram. So density will be higher. If I have, say, 1 milliliter volume of iron, metal, so here the weight will be too high. So it means density is too high. So that is one way to represent concentration. Similarly, the other ways, the one popular way is mass percent. How much mass out of total mass, how much mass of something is present. So the first one is mass percent. You already know mass of solute divided by mass of solution into 100. This is actually, if you understand diagrammatically, say you have water and you mix sugar in. So some sugar is there. And whole is solution. Whole is known as solution. Water is solvent. Sugar is solute. So solute is dissolved in solvent to get solution. Sugar is dissolved in water to get a sugar solution. So in this case, if we are asked what is the mass percent of solute, mass percent of sugar, we will say what is the mass of sugar, which is solute, divided by mass of solution, total. Mass of solution means mass of sugar plus mass of water, total, into 100. That will be mass percent. So if I write it in case of sugar, sugar solution, mass percent of sugar will be mass of sugar divided by total mass, means mass of sugar plus mass of water into 100. So this will be what we will be writing to get the mass percent of sugar. Now you might be asked the mass percent of water also. So mass percent of water, if you have already calculated mass percent of sugar, it will be 100 minus mass percent of sugar. Otherwise, if you have not calculated already, then it will be mass of water, because now we are calculating of water, so it will be mass of water at the top numerator divided by total mass, mass of sugar plus mass of water into 100. So whatever you are asked the percentage, mass percentage of, that will be in the numerator. Sum of all percentages will always be 100%. Next way, parts per million. This is actually something similar to percentage, In percentages, we calculate how many parts are there out of 100. If out of 100, 40 parts, we say 40%. Similarly here, we calculate out of 1 million. 1 million is 10 to the power 6. Instead of 100, in this formula here, you have 10 to the power 6, which is parts per million. So suppose we have 1 million 1 million particles total of a mixture. Okay. And in this mixture, say 25, and these are say molecules. Okay. We have these many molecules, total molecules. Okay, total. And out of these total 1 million molecules, 25 molecules are of say CO2. Okay. Then we will say CO2 is 25 parts per million. Means if we have 1 million parts, out of which 25 parts are of carbon dioxide. So concentration of CO2 is 25 parts per million, 25 in 1 million parts. So it is just unitary method you will apply in such questions. Suppose you have been given that you have in 50,000 parts, okay, 200 parts are of carbon. Okay. Calculate calculate concentration of carbon in parts per million. So your task will be to obtain how many carbon parts will be there in 1 million parts of total. So you already know the relationship. In 50,000 total, you have 200 carbon parts. So in one, it will be 200 divided by 50,000. Hence, in 1 million, 10 to the power 6, it will be 200 divided by 50,000 into 1 million. 1, 2, 1, 2, 3, 4, 5, 6, 1 million. So 1, 2, 3, 4, 1, 2, 3, 4, gone. 20,000 divided by 5, that is 4,000 ppm. So it's simply unitary method you will be applying everywhere. Instead of 100 in percentages, in ppm, you will calculate in 1 million. That's the only difference. Otherwise, it is same. Calculation is same, concept is similar. You just need to calculate out of 1 million. Next one, mole fraction. And this is again same thing as you have done fractions in your previous grades. Fraction, say I have 7 balls, and out of these, 3 are red, 2 are white balls, and 2 are, or say you have 8 balls, 4 blue. So fraction of red will be 3 by 9, fraction of white will be 2 by 9, and fraction of blue will be 4 by 9. So this is something you know. What you are doing, if you are calculating the fraction of red, you are talking about how many red divided by total, how many white divided by total, how many blue divided by total. The same thing you will be doing here, but for moles. Instead of balls, you will be doing for moles. So suppose you have a mixture in which you have 2 moles of oxygen and 3 moles of nitrogen. Okay, so mole fraction of oxygen will be number of moles of
2 by
oxygen
5.
divided by 2 plus 3, that is 2 by 5.
Yes, sir. 0.4 something.
Yeah. And for nitrogen, it will be 3 divided by 2 plus 3 total, that is 3 by 5. And sum of all fractions will always be 1. So 2 by 5 plus 3 by 5 will give you 1. Okay, so it is just simply fraction, but of moles. So how do you write it? You write it if you have A and B for components A and B in a mixture. Mole fraction of A, mole fraction of A will be denoted by XA. Okay, sometimes it is written in few books chi A also, because chi is also similar sign, Greek sign, not same but similar. XA will be number of moles of A divided by total moles, means number of moles of A plus number of moles of B. Similarly, mole fraction of B will be XB equals to number of moles of B divided by number of moles A plus number of moles of B, means total moles. So this will be the similar concept you will apply to get the mole fraction, which you applied in case of balls. Number of blue balls divided by total balls, number of white balls divided by total balls. So here same, number of moles of a component divided by total moles, number of moles of another component divided by total number of moles. So these formula you will be applying. You need to at least remember these two. You can write these directly. Okay, so these formulas are common, and if you use it, you need to first write this formula and then substitute the values. In case of A and B, suppose A is carbon dioxide, so you will write like this, that number of moles of carbon dioxide, like this. If it is number of moles of nitrogen divided by number of moles of nitrogen plus number of moles of oxygen, you will write it like this. But the concept is same, moles of that component divided by total number of moles of that component divided by total number of moles will give you fraction of moles, which is known as mole fraction. Now the very important part, and you need to be attentive here. If you don't understand this part, it will be difficult for you to solve the questions, majority of the questions of this chapter related to molarity and molality. Molarity is somewhat similar to density, but instead of calculating the mass in 1 milliliter, we calculate the moles of solute in 1 liter. So you know that the density is given by, if we talk about density, density is given by either in gram per ml or in kilogram per liter. Gram per ml or kilogram per liter. So kilogram per liter, if I say, it means in 1 liter, how many kilograms are there? If I weigh 1 liter of something, how many kilograms of the solute will be there? Solute. Okay. So understand the difference. If I have the sugar solution, I have water and I have sugar into it. So it is, if I have 1 liter of total solution, means water plus sugar, then how much mass of sugar is there? That is density. Now, if I say molarity, the difference is, instead of kg, I change it to mole, and then it becomes molarity. In 1 liter, how many moles of sugar are there? Then that will become molarity, and you know how to convert kilograms to mole. You need to just divide it by the molar mass after converting to grams. Given mass divided by molar mass will give you mole. If it was in kilogram per liter density, this kilogram can be converted to mole by first converting it to grams and then dividing it by molar mass. Given mass divided by molar mass. Suppose I have 342 grams, or say 0.342 kg per liter as density. So in 1 liter, I will have 342 grams of sugar. 342 grams of sugar will be 1 mole because it will be 342. Given mass divided by molar mass of sugar is also 342. Means the molarity will be 1 because there is only 1 mole present in 1 liter. So molarity will be 1. In simple terms, you need to understand if you have, say, 4 liters of something and it has total 16 moles of anything, to get the molarity, your job is to get in 1 liter how many moles will be there. So I can divide it in 4 parts. So 4 liter, every part will be of 1 liter, 1 liter, 1 liter, 1 liter. And every part will have 4 moles, 4 moles, 4 moles, 4 moles, total 16 moles. It means molarity will be 4 because in 1 mole, 1 liter, there are 4 moles of that particular compound. Any confusion? Let me know if there is any confusion. In simple terms, I am telling you, your task is to find out how many moles of a compound are there in 1 liter of the whole solution from the data given. Okay. Most of the
Sir,
time,
if the volume is like not exactly 1 liter, if the value differs, then will we then simply divide it by like moles upon volume by using that
uh,
unit method, sir?
no, in few cases we will do approximation. In few cases we will get the value. Okay, so you will see in the questions we will be doing that.
Okay, sir.
In few questions we can do approximation, and obviously there will be reason why we are doing the approximation. That is something I'll discuss later on. First, you need to understand what is molarity. In simple terms, it is how many moles are present in 1 liter of the solution. Next is molality. The difference is here molality. It was molarity. Now we are talking about molality. Molality is again the number of moles of solute, but in 1 kilogram of solvent, not solution. Understand the difference here.
Mass,
Here
sir. We have mass.
in molarity, it was number of moles of solute in 1 liter of solution, total solution. Solution is both solvent plus solute. However, molality is L, molality. Same
So
thing, number of moles, yes, just a second, in 1 kilogram, but of solvent only, not the whole solution. Yes,
what does molarity vary with temperature?
I'm coming to that again. Molality is in solvent. Molarity is in solution. Moles in solution. Molality is moles in solvent only, solvent part only, and weight of that solvent, mass of that solvent, not the volume. Okay. Now, the question is, why do we need molality? Why molarity can't serve purpose? This is because many scientists are working on, common objectives, and a few scientists are at very hot regions, for example, in India, hot regions of India or South Africa, and few are, say, Norway, where the temperature is minus 40 degrees Celsius or so, or maybe 0 degrees Celsius, 5 degrees Celsius. So in case of molarity, it depends on volume. and volume changes with temperature. Volume depends on temperature. It means in hot regions, the volume will be higher, that is denominator will be higher, and molarity will actually be lower than what a scientist will experience in colder regions. Because in Norway, Ireland, etc., the temperature is very low, volume will be low, denominator is low, hence molarity will be more than what is at higher temperature regions. So molarity depends on temperature. It is not independent of temperature. So if it is calculated at different places at different temperatures, its value will be different. And that creates some problem for scientists. Yeah. Hence the concept of molality. Molality is you need to calculate number of moles in mass of solvent only. And mass is independent of temperature. Whether you get your weight when it's winter or summer, your weight will remain constant unless you gain or lose weight. The weight of an object will remain constant at different temperatures. So molality is in that case, okay, has an advantage over molarity. So molality has advantage over molarity in case of different temperatures. So that's why molality has advantage over molarity as it does not change with temperature. Formula you have to remember which one is molarity, which one is molality formula. Again, going back, a quick recap before I start the questions. Mass percent is simply mass of solute divided by total mass into 100. Mass of one component divided by mass of all both components or three components, whatever components we have, total components into 100. Next, parts per million, it is nothing but how many parts will be there in 1 million total parts. Similar to percentage. In percentage, we have out of 100. In ppm, we have out of 1 million. Then mole fraction. Mole fraction is ratio of moles of one component divided by total number of moles. Fraction. Don't multiply by 100. It is just a fraction. It is not a percentage. So unless it is asked that you need to convert it into percentage, don't multiply by 100. Yeah. Then we talked about very important concepts, molarity, number of moles in 1 liter of solution, and molality, number of moles in 1 kilogram of solvent. Now the question. A solution is prepared by dissolving 2 gram of substance A in 18 gram of water. Calculate the mass percent of solute. And what is solute? Which one is less in quantity? 2 gram, 18 gram, 2 gram is less. It means 2 gram is the solute. How will you calculate the mass percent? You will write the formula. Mass percent equals to, first let me see, I'm getting few answers. Yes, Bedi, correct, yes. Mass percent equals to mass of solute, because here we have been asked of solute, so you will say mass of solute divided by mass of solute plus mass of water, equal mass percentage into 100. That is 2 divided by 2 plus 18 into 100, 2 by 20 into 100, 25s are 5 2s are 10%.
Yes.
Okay. Sub it is 2 plus 18 in the denominator, not
Yes, sir.
18. And that is many students initially make these mistakes, okay, that they just consider one as water as the total, which is not correct. Okay, next one. A solution is prepared by adding 60 grams of methyl alcohol to 120 gram of water. Calculate the mole fraction of methanol and water. Mole fraction of both. Methanol is CH3OH, water is H2O. So because we need to calculate mole fraction, and if you don't understand the question, always write like this. Whatever you have to calculate, write towards right on rough paper, okay? Mole fraction. How do you calculate mole fraction? Mole fraction you calculate by number of moles of A divided by number of moles A plus number of moles of B. It means you need number of moles. So you need moles for that. How do you get moles? Moles you can get from mass. How? Mass divided by molar mass. But you don't have molar mass, so calculate molar mass. 12 plus 3 plus 16 plus 1, 32. H2O 18. Okay. It means for methyl alcohol, moles will be given mass divided by molar mass. Okay. When you calculate, it will be 1.875. For H2O, moles will be, remember I am following this approach now, from mass to moles, and then from moles to mole fraction I will get. Moles of water will be given mass upon molar mass, that is 6.67. So I got number of moles of CH3OH and I got number of moles of H2O. Now from moles I can get mole fraction by formula. So mole fraction of methyl alcohol will be number of moles of methyl alcohol divided by total number of moles. Means number of moles of methyl alcohol plus number of moles of water. That is 1.875 divided by 1.875 plus 6.67. When you simplify this one, you will get 0.22 something. Okay. Similarly, number of moles of H2O will be mole fraction of H2O will be number of moles of H2O divided by number of moles of methyl alcohol plus number of moles of H2O, that is 6.67 divided by 1.875 plus 6.67. When you solve this one, you will get 0.78. Yes.
So we can directly subtract it from 1, like 0.
No, we can do. You can do. That's what I'm coming to. So if you see now, 0.78, it is just if you do 1 minus 0.22. So you don't need to just do this much calculation. That's what I said when I explained mole fraction, that sum of all mole fractions will always be 1. So you will get the value 0.22 and 0.78. That will be the answer. If any step is not clear, let me know. Yes, Devyansh, approximately correct. Yes, yes. Next question then. A solution is prepared by dissolving 18.25 gram of NaOH. NaOH is known as caustic soda, sodium hydroxide, caustic soda, in distilled water to give 200 milliliter of solution. Calculate the molarity of the solution. So first write the formula of molarity. Molarity is number of moles of solute divided by volume of solution in liters. It means you need moles of solute, moles of NaOH. Volume is given 200 milliliter. So moles of solute will be given mass divided by molar mass. You know that, divided by volume of solution in liters. Given mass is 18.25 and molar mass of NaOH is sodium 23 plus oxygen 16 plus hydrogen 1, that is 40, divided by 40 divided by volume of solution in liters, means 200 milliliters you need to convert to liter, means you need to divide it by 1000, so 0.2 liter. It means it will be 18.25 divided by 8. Okay. When you calculate, you will get 2.28 approximately. And the way how you write molarity, it is represented by capital M. So you write capital M after it, it indicates it is molarity. Or you can write grams per mole or 2.28, sorry, moles per liter, not grams per mole, moles per liter or moles per liter, like this. Liter.
Sir, is 2.25 accepted?
In this case, 2.27 will be accepted, not 2.25. That means there
Okay,
is
sir.
some more approximation. If anything is not clear, let me know. You just applied the formula. You need moles. Moles, you know, mass divided by molar mass. Why? Because mass is given. That's why you applied this formula. You have been given mass. You know molar mass of sodium hydroxide. So you will get moles. Divided by volume in liters will give you molarity. And because molarity is moles per liter, that's why the unit moles per liter. It is also written as capital M. Both are correct. So whether you write 2.28 capital M or 2.28 mole per liter, correct answer. Okay, so I hope it is clear then. Next question. How many moles and how many grams of sodium chloride are present in 250 milliliter of a 0.5 m NaCl solution? Now this question looks slightly complex, but it is very easy.
So we can
Sodium chloride.
multiply moles and volume in liter to get moles.
Exactly. Because molarity is equal to number of moles of solute, obviously, divided by volume of solution in liters. And when it is given like this, it is actually the volume is 200 milliliter and the molarity is 0.50. Capital M indicates molarity. So what you have been given, 0.50 is molarity. Number of moles you have to calculate according to question, how many moles, divided by volume. Volume is 250 milliliter, that is 0.250 liters. You have to keep the volume in liters. Means number of moles will be 0.250 into 0.50, that is 0.125 moles. 0.125 moles. Now, how many grams also has been asked? How many grams? And you know, mass is moles into molar mass. From the conversion diagram, if you convert moles to mass, you multiply by molar mass. So number of moles 0.125. Molar mass of sodium chloride will be 23 plus 35.5. 23 atomic mass of sodium, 35.5 of chlorine, means 0.125 into 58.5, 58, 12, 72. So around, 7.3 something it should be there, okay? Grams. Correct answer, 0.125 moles and 7.3125 grams.